Good afternoon, my name is Thilo Theloy and I will present a pilot project for de-icing with deep energy wells at the Oslo Airport, Gardermoen. Overview of my presentation. I will give some introduction to the project at the airport. I talk about how deep energy wells work, present the well construction, about the well operation and our experience with the wells, and I present the potential of deep energy wells with other applications. Here on this side you see a satellite picture of the engine test area where the airplanes are testing engines after repair or maintenance. This is heated up by a glycol loop during winter to maintain this ice free so the airplanes don't start sliding. The glycol loop is heated up by an electric boiler. Heat central is here, and our scope was then to drill 2 wells to 1,500 meters in this area to replace the electric boiler. And the main idea is there to reduce cost. We have a much lower energy consumption, and also to avoid power peaks in the network, which become quite expensive during winter time. The total project cost was 18 million kroner, including technology development, like a test rig. We had a budget for innovation this was used for rig upgrade, drilling technology and also collector installation. And this covered also the project cost. Innovation Norway supported the project with 40% public funding. We started planning in September 2017 and commenced drilling in November 2017. The wells were finished in spring 2018 and startup was in November 2018 when we handed the wells over to the Oslo Airport. Down here you see another picture of the engine test area. Here's our team, and back here are 2 cars parked, so it's about 4,000 square meters here in the center, which is heated up. So how do deep energy wells work? We drill a vertical hole into bedrock to about 1,500 meters, run a center pipe into the well and circulate water along the open rock surface down into the well and up the center pipe, and by circulating the water along the surface of the rock we heat it up, and then it is pumped to a heat exchanger where the energy is taken over by the glycol loop, and the colder water is returned into the well. Regarding Gardermoen, this had a little bit special geology for Norwegian conditions, relatively thick overburden with unconsolidated glacial river sediments, and below that the Precambric gneiss, which was our actual target. The temperature gradient in the area is about 16 to 18 degrees per 1,000 meters, and based on that we expect a production temperature of 12 to 14 degrees from the well. So we don't get, when we have at the bottom of the well 30 degrees, we don't get 30 degrees out of the well. We only heat up the water with the rock and get a slightly higher temperature than we inject into the well. And to cover the energy demand we need 2 wells to keep the engine test area ice-free. For drilling we plan to use a 27-ton hook load foundation drilling rig, air percussion drilling with down-the-hole hammer, 3 compressors and 1 booster. For drilling through the overburden we applied casing drilling, which is a normal foundation drilling method with ring bit. And as soon as the bedrock was confirmed, we would pull the center bit from casing drilling and run in with a 6.5-inch bit and down the hole hammer and continue drilling to 1,500 meters in a single section. After that we would clean the well, install the center pipe and the submersible pump, and install everything around the wellhead and hook this up to the heat central with insulated pipe. And in the heat central, we would only use a filter system and a heat exchanger. We would not require a heat pump, which is kind of the key of the system, that you can use direct heat for keeping areas ice-free. Now we come to the well construction. You see some impressions here on the right. This is the foundation drilling rig from Bosum Boring, which conducted the drilling operation. Here you see also a smaller rig which drilled in parallel on the second well. Between the wells is about 40-meter distance to keep the energy production separate, that the wells don't take energy from each other, and also to avoid during drilling incidents that air would go from one well to another well. So the casing drillings through the unconsolidated sediments went as planned. This is something Bosum Boring is doing as a standard operation, and we encountered bedrock at about 80 meters depth on both wells. After that we encountered several fractured zones with water influx. We tried to cement them off, but with limited success. Sometimes it's quite large fractures, and you have to limit the amount of cement you pump that you avoid contaminating the neighboring well with cement. So we continued drilling with about 10 cubic meters per hour water influx. We used a small booster, you see this one here, from about 350 meters to about 800 meters. It was then later realized that the booster was too small, and which limited the drilling progress significantly. But we also noticed below 600 meters that fractures became rare and water influx stayed constant, so the surface weathering is limited to about 600 meters in this area. And there we could tune in on the drilling parameters and got good drilling progress. From 800 meters on, we used then the bigger booster, which you can see here was offloaded from the truck. We rented this from the UK. This one was the right size, and we had significant improvement in drilling progress there. But then again, below 1000 meters, we had to spend more and more time on connections, keep the hole clean, and after the connection to get the water up to speed again, and the overall ROP was reduced again. Both wells drilled almost perfectly vertical to 1500 meters, one to 1508, the other one to 1520 meters. And after cleaning the wells thoroughly, we demobilized the rig, and NGU came and logged the wells about 4 weeks later. And we got confirmation on temperature of about 28 degrees at 1500 meters, which was a little bit colder than hoped for, but within the simulations. After that, the center pipe was installed. This was a very well planned operation, and each well took about 5 days to install the center pipe, and it was pretty much without any issues. We had only at one time that the submersible pump was a bit difficult to install, but we had just to remove some thicker welds on the pipe that we could get the submersible pump down. Regarding the operation and experience, the wells were tested with the test rig after the collector or the center pipe was installed. The test rig confirmed our simulation models and the energy production from the wells, and with that we handed over the wells in November 2018 to the Oslo Airport, to Avinor. And in November we had then a successful startup, as you see down here. After the first snow, we had a nice snow and ice-free area. After a while we got challenges with the filter setup, especially after the summer period, that the fine filter was clogged, and this was mainly due that the fine filter was too fine for the application, and also it was not very user-friendly to clean. So we improved now the filter setup with a better filter solution, which is easier to clean and with a better sized filter. and also establish an operational procedure that the wells should be circulated during summer every few weeks, that you avoid organic growth in the stagnant water near surface. All this took quite some time due to different focus by the airport, mainly not due to COVID, but we have the wells now ready for this new winter season and expect full operation there. Here you also see the heat central with the heat exchanger, the electric boiler, and these are the 2 electric pumps for the surface loop. About the potential of deep energy wells, we talked now about the direct heat approach, where we use the wells without a heat pump, which is, in my opinion, the most attractive application. You reduce operational cost by 80 to 90%, as you only have the submersible pump in the well circulating the water around. And the wells produce, due to the depth, we drill them to 10 to 15 degrees, depending on where you are and how fast you circulate them. And this temperature is sufficient to keep football fields ice-free. There are about 3,000 football fields in the Nordic countries. Pedestrian areas is another big market. Airports have different applications. We talked now about one application. Critical parts of roads, for example bridges during winter times, and also warehouses, for example, which don't need 20 degrees or 25 degrees. It's sufficient to keep them ice-free for storage. Is an interesting application. Of course, you can add a heat pump, and with the heat pump you can raise the temperature to new level where residential building, hotels, hospitals, and also agricultural applications can make use of these wells. If you want cooling, you have to add shallow wells, as these deep wells are not suitable for cooling. But with a combination of some shallow wells and, for example, 2 deep wells, you can cover pretty much all energy applications. Thank you very much. This was all from my side. Do you have any questions?